So we've defined what we mean by a basis. A basis for a vector space is a collection of vectors that span that vector space, and also the collection is linearly independent. Incidentally, notice that I'm requiring that this collection of vectors actually have an order associated with it, not just being a set, but actually a list of vectors. And there's kind of a technical reason for that we'll get to eventually, but for now, the distinction isn't super important. But when you have a basis, generally, when you write them down in an order, you should keep them in that order. Anyway, let's look at some examples of a basis, just so that we are sure we understand what this idea is saying. So first of all, let's look at this vector space. So in R3, the vector space of vectors that have anything in the first and second entries and a 0 in the last entry. And let's look at all of these things. Now, any of these might be a basis. And let's just go through and think about, for each collection of vectors, is it actually a basis or not? All right, so for this collection, right, we need to check, to answer the question, is this a basis, we need to check, is it linearly independent? So to check if these are linearly independent, technically we would need to check, is there some non-trivial linear dependence relationship between these? But, again, when we have only two vectors, we can just ask, are they multiples of each other? And clearly they're not in this case. So yes, these are linearly independent. And now we need to ask ourselves, do they span V? Okay, and probably you might be able to see that the answer here is yes. If you really want to write things out, you can actually parameterize this vector space in the way that we have been doing. You can break it down as A00 plus 0B0. So this is A times 1, 0, 0 plus B times 0, 1, 0. And so now you can see, well, look, any vector is spanned by these two, which are exactly the vectors in this collection. So yes, these two vectors do span B. So since they're linearly independent and they span V, that means we have a basis. These two vectors form a basis. All right, so what about this one? So we have to ask the same two questions. Are these linearly independent? Right? Is there some non-trivial linear dependence relationship between these? And probably just by looking at it, you can tell, yes, there is a linear dependence relationship, a non-trivial linear dependence relationship, because 1, 1, 0 is equal to the sum of 1, 0, 1, 0, 0 and 0, 1, 0. Right? This is a non-trivial linear dependence relationship. If you wanted to, you could move this one to the other side to write, the 0 vector is 1, 0, 0 plus 0, 1, 0 minus 1, 1, 0. So there's your non-trivial linear dependence relationship. So are these linearly independent? No, clearly not. So this isn't a basis for V. All right, what about this collection of vectors? Well, first we need to ask, are these linearly independent? Well, any singleton collection that isn't the 0 vector will be linearly independent, right? So yes, this is linearly independent. So does it span V? Well, just kind of by inspection, by looking at this, you can probably tell that the answer to this is no, because the vector 0, 1, 0 is not spanned by this collection. 0, 1, 0 is not in the span of 1, 0, 0, right? So this, since it's linearly independent, it's a basis for something, but it's not a basis for V, right? Okay. Finally, let's look at this example. These three vectors, are these linearly independent? You can probably tell that yes, they are. I won't drag you through details here, but yes, these three are linearly independent. Do these span V? Well, this time the answer is no again. And but the answer is no in a slightly different way. The reason that these don't span V is because this time we have a vector in our span of these three, right? So 0, 0, 1 is definitely in the span of these three vectors. 1, 0, 0, 0, 1, 0, and 0, 0, 1. But this vector 0, 0, 1 is not in V, clearly, right? V, every vector in V has a 0 in its third entry. So this vector doesn't have a 0 in its third entry, so it can't be in V. So this isn't a basis for V either, because again, it's linearly independent, so it spans something, but it doesn't span V, right? It's sort of too big, right? So this first example, this is a basis for V. And the second one is not, because it fails to be linearly independent. The third one is not, because its span is too small. It doesn't span V. And the fourth example here is not a basis for V, because it's linearly independent, but its span is too big, right? Its span contains V and is actually bigger than V. Now, something that probably isn't totally obvious, or might not be totally obvious at this point, is whether every vector space has a basis. So, you know, for subspaces of Rn, probably you can convince yourself that yes, every subspace does have a basis. In fact, for most vector spaces that you might want to write down, you can probably come up with a basis. For example, Pn, you might be able to come up with bases, or Mn, M, I guess I usually write these backwards, M sub Mn, matrices with M rows and N columns. You might be able to come up with a basis for that as well. But there are actually some vector spaces where it's not really obvious if it's possible to write down a basis. So as an example, consider the vector space of all functions whose domain is real numbers and take real values. So if you think you can write a basis for this, I would challenge you to, even if you allow yourself to write down a basis that's infinitely large, which you would have to do for this vector space, it's going to be very difficult to actually write down a basis. But in fact, every vector space does have a basis. Although to prove this, you actually need a kind of delicate assumption about how sets work, which is called the Axiom of Choice. And I won't get into that. But rest assured that if you accept the Axiom of Choice, which probably you should well, I don't know if should is the right word, but it's a common technical assumption that the Axiom of Choice is accepted, then every subspace does have a basis. Of course, the common vector spaces that, I should say every vector space. Of course, the common vector spaces that we work with, like these, we can actually write down a vector space, or write down a basis. So in those cases, there won't be any question about if there is a basis or not, because we can actually explicitly produce one. All right. Well, let's look at some examples of finding bases, some more examples of bases. So for P2, right, this is the collection of polynomials of degree less than or equal to 2. Every polynomial of degree less than or equal to 2 is going to look like a plus bx plus cx squared for some real constants a, b, and c. And so, you know, this is just another way of saying that 1x and x squared span P2. So since this collection where a, b, and c are real numbers, this is exactly P2, but this is also the span of 1x and x squared, right? So we have a spanning set for P2. Now we have to ask, are these linearly independent? So is there any non-trivial linear dependence relationship? So we're asking about linear independence. So let's write down a linear dependence relationship. So that would be a times the first one plus b times the second one plus c times the third one. Right? Here's a linear dependence relationship. Is it possible that A, B, or C could be non-zero. Well, no, for these two polynomials, the one on the left and the zero polynomial on the right, for these to be equal, we must have A equals 0, B equals 0, C equal to 0. And so that means the only linear dependence relationship among 1, x, and x squared is the trivial linear dependence relationship, and that means that these are linearly independent. Right, so that demonstrates that this really is a basis because it spans P2 and also it's linearly independent. All right, well, let's look at an example from matrices. So how about M2,2, so the vector space of 2x2 matrices. So here's a basis for this vector space. Again, I won't write it out. You can probably convince yourself that every 2x2 matrix is a linear combination of these, because A, B, C, D is A times this one plus B times that one plus C times that one plus D times that one, right? So these span M2. So we have a spanning set. And then are these linearly independent? Again, I won't write it out, but if you write a linear combination of these and set it equal to 0, the only way to make that happen is for A, B, C, and D to be 0. So linear independence also holds. So that means that this genuinely is a basis for M2,2. All right, so for these two examples, probably you could have come up with these two bases for yourself. Let's look at some examples where maybe it isn't quite so obvious how to find bases. So here's an example. Let's find a basis for the subspace of R3 whose entries satisfy this equation. So A minus B plus C equals 0. All right. Well, one way to do this is to get a better description of what all of these vectors are. So, right, there's this relationship between the entries of these vectors. What we can do is use this relationship, rearrange this relationship to tell us what A is. So A has to be B minus C. If you had other equations that you needed to, or other relationships between the entries in this vector, you could add those and then do some sort of row reduction to get a good description of pivot variables in terms of free variables. Right here we have free variables, and they're telling us what the non-free variable has to be. So another way to write this set is, now that we know if we write it this way, B and C are free, we can write this subspace as A is B minus C, and then B is just B and C is just C. And here B and C can be any real number. Okay. Now that we've written it this way, we can play our usual game to see, right, we could write this as 1, 1, 0 times B plus minus 1, 0, 1 times C. Right, that's the same as this vector. So that shows us that this subspace we're working with is spanned by the vectors 1, 1, 0 and minus 1, 0, 1. So now we have a spanning set. To check if it's a basis, remember we need to know, is this spanning set linearly independent? Well, we only have two vectors, so as long as neither is 0 and one is not a multiple of the other, then they are linearly independent, and that's clearly the case, right? You can tell that just by where the 0 entries are in these vectors. So this collection of vectors 1, 1, 0, here we go, 1, 1, 0, and minus 1, 0, 1. These are linearly independent, and they span, so they form a basis. So we've found our basis. It's this right here. All right. For another example, let's look at P2. How about the subspace of P2 that is formed by all of the polynomials that when you plug in 1, you get 0. So all of the polynomials that have 1 as a root. If you don't see that this is a subspace, maybe you could check. All right, so, well, how to describe such a collection of polynomials? Any polynomial in P2 we could write like a plus bx plus cx squared, right? But now let's add the condition that our polynomial has to be 0 when you plug in 1 for x. So p of 1 equals 0. That means that, well, let's plug 1 in here for x. That would give us a plus b plus c equals 0. Well, look, this is kind of like in our previous example. This is a relationship that tells us something about a, b, and c. So we can use this to, we can rearrange this to phrase it in terms of pivot variables and free variables. So a is minus b minus c. And that means that our polynomial has to be minus b minus c plus bx plus cx squared. All right. So how could we write this? What we need to do is rewrite this in a way that makes it clear what polynomials we need to span this set, right? So this space that we're talking about, it's the set of all polynomials here where b and c, right? B and c are free variables now, so they can be any real number. All right. Well, to see what polynomials we need to cover all of these, we can play our usual game of trying to separate all of these terms based on what free variable shows up. So we have the terms with b's, so there's minus b plus bx, and then there are the terms with c's, so there's minus c plus cx squared. Okay, but now we can factor out the free variables, so I don't want a minus sign there. So there's b times minus 1 plus x plus c times minus 1 plus x squared. Okay, so now what we've shown is that every polynomial of this form, so every polynomial in our subspace, is a linear combination of these two. So that means this subspace is actually the span of minus 1 plus x and minus 1 plus x squared. All right, so now we have a spanning set. To know if we have a basis, we have to check if these are linearly independent, but again, we only have 2 of them. Clearly, one is not a multiple of the other because, right, if you take a scalar multiple of the first one, you never get any x's, so it can't be this. Sorry, if you take a scalar multiple of the second one, you never get any x's, so it can't be equal to the first one. And if you take a scalar multiple of the first one, you never get any x squareds, so it can't be equal to the second one. So these two are clearly linearly independent. And so now we have a basis, right? Minus 1 plus x and minus 1 plus x squared form a basis for this subspace over here. All right, one last example. Let's find a basis for this subspace of M2,3. So I will insist that there be zeros in these, but also we have these relationships among the non-zero entries. All right, well, as in the previous example, we can use these relationships to change our description of what these matrices are in a way that will, we'll split them into non-free variables and free variables. So our relationships are a plus 2b, I guess I'll write it down, a plus 2b minus c. No, let me not write it down. So because we have these two equations, right, what we really have is a system, linear equations, right? Each of these is a linear equation. And to rewrite a linear system in terms of non-free and free variables, we just need to do a row reduction, right? So this is a homogeneous system, so we don't need to write down the augmented matrix, which is good because turns out this wouldn't be a vector space if these weren't equal to 0. So let's write down the matrix for this system. I'm just reading the coefficients off of these to get each row of this matrix. So 1, 2, -1, and 4. And then for the second equation, 0, 1, -2, and 2. And now we need to row reduce, which fortunately is just a matter of a single row operation. So row 1 minus 2 times row 2, and that'll get us to reduced row echelon form. So 1, 0, 3, 0, and then 0, 1, -2, 2. Okay, so now this is in reduced row echelon form, and so this tells us that A has to be minus, sorry, let me write this vector style. No, I don't need to. Sorry, I don't need to. So this tells us that A has to be equal to -3B, and it tells us that, -3C, right? This is the column that represents C. And then B has to be 2C minus 2D. Okay. All right. Now that we have non-free variables written in terms of free variables, we can re-express what this matrix looks like. So this collection of matrices is the collection, so A has to be -3C, B has to be 2C minus 2D, and then 0, 0, C is free, and D is free. Okay. And again, the key thing here is the reason that we've done this is now C and D are free variables. They can be any real number, and there are no more relationships, right? No more hidden relationships between the entries. All of the relationships between the entries are now explicit instead of implicit like they were before. Okay, so as in our previous examples, now we need to write this general form that we've figured out, express this as a linear combination of two fixed matrices. And probably you can see that this is C times the matrix -3, 2, 0, 0, 1, 0, plus D times 0, -2, 0, 0, 0, 1. Okay. So if you don't see why this is true, compute what this matrix is. You'll see it's just that. All right, so this tells us, now I'm running out of room here because I don't want to scroll down. This tells us that this space of matrices up here is equal to the span of these two matrices down here, -3, 2, 0, 0, 1, 0, and 0, -2, 0, 0, 0, 1. Okay. And now we have to answer the question. So we have a spanning set. Are these linearly independent? Well, again, clearly just because of the placement of non-zero entries, and also because there's only two of them and they aren't multiples, we can tell that these are linearly independent. So we have a basis, right? These two matrices together form a basis for our space of matrices. So these form a basis for this subspace.